All right, so let's look at another geometric method in terms of trying to calculate slopes and deflections on sections of a beam. All right, we we have already looked at the moment area method, and I had mentioned in previous weeks that the moment area method and then the conjugate beam method, which is what we'll be looking at today. Oops. Conjugate. So it's like French, right? Conjugate beam method. So it is a geometric method. So it's similar to the moment area. The moment area method. Okay. So because they are similar, it requires the same amount of computation. Um, and then the goal is that it's also used to determine slopes, used to determine slopes and deflections. All right. So that's something to take note of. So a lot of the conjugate beam method is based on the moment area method. All right. But then it's I find this method fairly straightforward compared to the moment area method in the sense that you don't need to be finding like, yes, you might have to draw the elastic curve and all that, but in the moment area method, if we recall, the elastic curve was so critical because we needed that to be able to find slopes and many moments. I mean, slopes and deflections by looking at the moments of the M over EI diagram, which could be a bit confusing sometimes. All right. We'll go ahead and look at what this method is all about. I think it was developed by Muller Breslau. Muller Breslau or Breslau, I think in one of the 1865. All right. And it's been in use since. All right. Before the advent of computers, most calculations in engineering were done by hand. All right. So the geometric method, the conjugate beam method were hand calculations, or they were developed as hand calculations to make it easier to calculate. All right. And then but then with the advent of computers, now we've moved more into more complex calculations using the stiffness matrices and the flexibility matrices, which I think we'll learn in structural analysis next semester. All right. So, I mean, yeah, these methods are old. So technically, in the most computer programs, you don't find them being used, but they are still a very useful tool to do very simple hand calculations. Okay. I think I also mentioned a few weeks ago that usually when you have to design a structure, all right, um, even when using a software program, maybe you're using some Prota or STAAD or ETABS or SAP or whichever engineering product that you have at your disposal, you still need to do some hand calculations to see if they agree with whatever output the computer has. All right, so that you are at least confident of the information outputs from your computer. And some of these methods are important in coming up with some of these solutions. All right. We so it's pretty much relies on the principle of status. I can just relies on the we have developed some few equations. I'll go through them. We know that if we differentiate the shear with respect to x, we get the load intensity. All right, I'll explain. And then also, if we differentiate the slope with respect to the distance x, we get the m over ei diagram. Okay, these have been established already in our previous calculations. All right. And then if we have moment, okay, so if you have moment, and then we differentiate the moment with respect to x, okay, differentiate. Um, so we differentiate with respect to x, which means we have what? We have the m dx. So the m dx will give us what? V, right? If you differentiate the moment with respect to x, you get v. Now, if you differentiate again, okay, so another differentiation with respect to x again. So that's, let's say, the squared m, the x squared, which is the same as the v, the x, you get w. Okay. So technically, the squared m over the x squared is the same as w. So pretty much these two are the same, right? One, you are differentiating the moment, which means that you need double differentiation, and then one, you are differentiating the shear, so it's only one differentiation. Okay. In the same way, so with these first two equations, so let me label it equation 1 and equation 2. They are, so equation 1 and 2 are based on the loads. Okay. So the external loads on the structure, right? So if we differentiate the moments or the shear or the internal loadings of the, sorry, not external, the internal loadings of the structure. And we also agree that these loads, they cause deformations. Okay. Anytime we have a system and then we apply a load on it, the system will cause some deformation. All right. And these deformations are slopes and then deflections. Okay. So some might even say displacement, because I think displacement encompasses both deflections and then slopes. Okay. And these loads can either be shear or bending. So which means that there's a relationship between the loads being applied and the deformations. Okay. And that's what we've been trying to do from when we're looking at the moment area method, looking at that relationship between the deformations in the system and then the moments applied. All right. So we know that the theta over the x is equal to MEI. And then we know that the deformation. So, for example, if I have something like this, if this is x and this is y, some books will say v is fine, whether it's v or y. I mean, small letter v, okay, or y, it indicates the deformation. So as I move from x from A, sorry, let me just go back. As I move from A to B, my deformation can easily be calculated. At A, my deformation is 0. At C, my deformation is maximum. And then as I go to B, the deformation will slowly decrease to 0. All right. So the curve here, the elastic curve here, is a plot of the deformation along the various points of the beam for every x. All right. So this elastic curve equation, we also saw it to be the squared y over the x squared to be equal to m over ei. Okay, and this is what we called, I think last week or the week before that, this is what we call the elastic bending equation, or the Euler-Bernoulli equation, right? So now if you look at these 4 sets of equation 1, 2, 3, and 4, there are similarities between them, all right? So equation 1 and 2 are based on the loads, and then equations 3 and 4 are based on the deformation. Okay. All right. So there's some similarities or some comparison between these 2 equations, right? Which means that if you look at equation 1 and 3, okay, but let me also write another set of equations for us before we move to the comparison. So this is for when we are differentiating, right? So in all these cases, we're doing differentiation. Now let's look at some other option where we do integration rather. Okay. So if I take equation 1 and I do my integration, so let me just name it integrating or integration. So if I take my equation 1, I integrate the v dx, then it means that v is equal to w dx. If you integrate your load intensity, you get the shear. Okay. And that's like normally when you have a beam that has a UDL on it, you find the area of the UDL. All right, so it's the area under a curve. Integration is simply area under a curve. Okay. Then if I integrate equation, so let me call this equation 5. If I integrate equation 3, then it means that my slope theta is equal to m over ei dx. And this is the first theorem of the moment area method. Okay, so let me call this one equation 7 because I want to do that. I want to. Then if you do the double integration to get m, then it means that our moment m here is simply double integration of w dx. Okay. Then our deflection y, or some books will use small letter v, is equal to, again, double integration of m over ei dx. Okay. So now if you take a look at it, you can compare. So this is equation 6, this is 8. So we can compare 5 and 7. So let's compare 5 and 7. Okay. So we can see that 5 and 7, we can assume that v is equal to theta, and then w is equal to m over ei. All right. So it means that v can give us theta or vice versa, and then w can give us m over ei. Okay. Now, if you compare 6 and 8, okay. So again, you can look at something like this. You would realize that 6 and 8, the moment can give us the y, which is the deflection. So Or deflections can give us the moment. We look at why this comparison is important. And again, we can see that our W is to M over EI. So that has not changed. Okay. Now, because of this correlation between these 2 points, or I mean, if we compare the so if we compare the shear with the slope, and also we compare the moments with the displacement, which we have over here. So here we are comparing moments. We compare moments with displacement. Moments with displacement or deflections. And then this one, so we compare shear with slope. Okay. Then here we compare, what's the name? We compare the load intensity with the moment, or with the M over EI. So these are comparisons between loadings and then deformation. So let's see how useful these are to us. Okay. So if we have a beam, okay, and it has some loading on it, it could be some loads. We don't know what loads these could be. Okay. So this is W. It means that this beam here, which has W and it has a length L, to end up giving us another beam with some moment. So this is the moment. Okay. So again, this is the same length L. So this this gives us the moments diagram, or to give us the M over EI. So this diagram is M over EI. Okay. So what we are looking at, this is the real beam with the load, and then this is its bending moment diagram. So for example, if we go back to what we had in some of our calculations like this, let me just go a bit of back and forth. So it's like we have yeah, right here. So we have a beam. So this is the beam, and this is its bending moment diagram. Or into bracket, if we divide it by EI, then it becomes the M over EI diagram. All right. So that's, I think, what we had here in the end. So this is the M over EI diagram. Okay. So in our case, we are looking at a more general approach where we have some general loading on the structure. Okay, so the load will give us the M over EI diagram. Okay. And then we are saying that if we take this M over EI diagram, okay, so we take this M over EI diagram, and then we use the M over EI diagram as a load instead of the original beam. We could develop some theorems or some equations from it, which would be useful to us. Okay. So I can then call this beam a conjugate beam. Okay, just giving it a name. All right, it's not a real beam. The real beam is there, but I'm trying to load a beam which has the same dimensions as a real beam with the M over EI diagram. So once I do that, I can call that particular beam the conjugate beam. And what this does to us is that when you compare the two beams, all right, we know that for the two beams, we mostly will find shear and then find bending moment. Okay. But for the conjugate beam, where we are using the M over EI diagram, we would find the slope and then the deflections. So some books will use this or delta. So here, the Y can also mean delta. All right. In case we are looking at the Y can also mean delta. Okay. So based on that, I can write two theorems. And then the first theorem, so we should know what these theorems are. All right, I think sometimes I do ask the students to state some of these theorems in the exams. So the theorem one says that the slope at a point, okay, in the real beam to the slope at a point in a real beam is numerically equal to the shear at the corresponding points in a conjugate beam. Okay. So let's look at it. Now, if I have a beam, okay. So this is my real beam, right? Which we are. Let's say I want to find the slope at K. Okay. So I know that if I have a beam, so this is my deflected shape or the curve, and I want to find, so let me draw a tangent at K. Okay. And I want to find this angle here, theta K. Okay. So the slope at K in the real beam is saying that if I take my conjugate beam, okay, and then I come to the conjugate beam and I find K, and I look at point K. If I look at point K, the shear force at point K, the shear force at point K in the conjugate beam. So the shear force at K, which is VK in the conjugate beam. So let me say CB. Okay, CB stands for conjugate beam. So in the conjugate beam is equal to the slope K in the real beam. Okay. So to not confuse you guys, let me just flip these two. It doesn't really affect us that much. All right. Let me just flip these two so that it makes it easier for us. So that if you're looking for theta in the real beam, that theta corresponds to shear in the conjugate beam. And then if you're looking for the deflection delta or y in the real beam, that corresponds to the moment at that particular point in the conjugate beam. All right. So the first theorem is saying that if I want to find my slope in the beam, in the actual beam that I have, if I'm able to create what we call a conjugate beam, then based of that, if I find the shear force at that same point in the conjugate beam, it will give me the slope in the real beam. Okay, so we'll look at some examples. Now, the second theorem, which I think by now we should all be aware what it is, states that the displacement or deflection of a point in the real beam is numerically equal to the moment at the corresponding point in the conjugate beam. Okay. So back to the same K. All right. So if I want to find the deflection at K, so I want to find this deflection here, right here. So delta K. All right. So I'm being told that if I want to know delta K in the real beam, then I need to find the bending moment at K in the conjugate beam. Okay. If I'm able to do that, then I have my displacement. All right. It is, yeah, so that's what it is. Okay. So let me just go over whatever we've discussed so far. We're looking at the comparison between deformations, and then I think it has to do with what you call it, continuity equations, right? That's a There are a series of equations that relate low stresses to deformations, right? Which I think you should learn a bit of that in your strength of materials class. Okay. So if we go back to our equations here, equations 5 to 8, we can see that slope correlates to slope correlates to shear, and then displacement correlates to moment. So it means that if I can find the slope in the real beam, it's equal to the what's the name? The moment in the so if I can find a slope in the real beam, it's the same as the shear in the conjugate beam. And then also if I can find the moment in the conjugate beam, is the same as finding the deflection in the real beam. Okay. So the comparison has to mostly comes down to comparing equations or comparing this right here. Okay. So it means that whilst I'll load my real beam with the actual load intensity, which is W, if I can load the other beam, which we call the conjugate beam, it's just should I say an imaginary beam you are creating to help you to solve your questions, right? So imaginary in quote. So it's not the actual beam, it's just something that you are creating to help you to solve your problems, right? So that beam, you load the beam with your moment diagram, which you call the M over EI diagram. All right. Now, for all of these to make sense, for all of these to work, we need to understand a few things also. One of them is to understand what we call the conjugate beam supports. Okay. So let me write that here. Conjugate beam supports. Okay. And these supports come about as a consequence. I hope I can spell that word. As a consequence of the two theorems. So of theorems 1 and 2. Okay. So basically, we want to develop supports which reflects these two theorems. All right. So let's look at, let me just do a table kind of thing over here. Okay, so let me see real beam. And then this is conjugate beam. Okay. So let's say if I have a beam, okay, and the support is a pin. So this is a pin support. Okay. pin supports. All right, we know that if you have a pin support, um, this is the elastic curve, right? Okay, so it means that you have theta. So there's theta, all right. But then the deflection, so we have theta, but then the deflection at A is 0, right? Because so if let me call this point A, we know that if it's a support, all right, the deflection at that point is 0. Just take you guys back to something. I don't know which, I think it was lecture 2 or 3. Which one was it? So lecture 3, I believe. I thought there was one that we discussed these support conditions. I wasn't here rather. Okay. Sometimes finding things can be a bit funny sometimes. Okay, yeah, I think it was here. So we can see from our lecture 2 that if we have a pin support, right? Once the support is pinned, the deflection at that point is 0. But then there'll be a rotation of that particular point A. Okay, at least we have established these things already. So I'm going to pick that information and bring it to this approach, the conjugate beam approach. Okay, so it means that based on what these conditions and what these conditions are, so maybe I can say that this is not equal to 0, so that it makes things easier. So based on these conditions, I need to come up with a support condition whereby the shear force will not be 0, and also the moment will be 0, because remember, slope correlates to shear, and then delta, which is deflection, correlates to moment. All right. So if I can find the moment at, sorry, if I can find the shear force at A on the conjugate beam, then that value should give me the slope. That's what the first theorem states. All right. So if the slope in the real beam is not 0, then my shear force in the conjugate beam should not also be 0, or shouldn't be 0. Okay. If the deflection in the real beam is 0, then it means that the moment in the conjugate beam should also be 0. All right. And the only support that satisfies this particular point here is if the support is a pin support or a roller support. Okay. So we can also draw one for a roller support easily. Again, have a elastic curve. This is theta. So it means that, again, theta A or theta. I'm going to just forget about those subscripts. It don't really matter that much. Okay, so theta and delta. All right. So theta is equal to 0. Let me just put some lines in between. Okay. So theta is equal to 0. So it's not equal to 0, and delta is equal to 0. So again, we need something similar, and it pretty much ends up being the same thing. All right. So here V is not equal to 0, but the moment is equal to 0. Okay. Now let's look at some other support conditions. So let's say we have a beam where the end is fixed. So this is a ruler, and this is fixed. Okay, so we are focusing on the left end and not the right, because the right end is free, but our focus is on the left end. So once it's fixed, we know that when the end is fixed, this is how the elastic curve looks like. Okay, so it means that our theta is 0, and our delta is also 0. Okay. So based of that, we need to draw a beam whereby the shear at that point is 0, and the moment at that point is 0. And we can only draw a beam whereby the end is free. So it means that if it's fixed supports in the real beam, it becomes a free support in the conjugate beam, or a point whereby there's no support. Okay. Now let's look at some more options. Okay. So what if in a real beam, what if in a real beam is free? So this is now free in a real beam. In a real beam, when it's free, if I'm to draw my curve coming from somewhere, it can look something like this. It means that I would end up with some deflection and also end up with some, if I'm to draw a tangent, at that point, I'll end up with some rotation theta. Okay, so it means that for this point, theta is not equal to 0, and delta is also not equal to 0. Okay, so it means that we need a support conditions that will support this information. So it means that then that end, which used to be fixed, which used to be free in the real beam, will have to be fixed in the conjugate beam so that our shear will not be 0, because then we can have shear and then moment. Okay, here we only have the shear. Okay. So our shear force or whatever will not be 0, and our moment will also not be 0, or there will be values for our moment. Okay. There are other options available to us, other examples. So I'll do one more. So where you have, if you have, let's say, a beam whereby you have what you call an internal support or internal hinge, or let me make an internal support. Okay, so a pin support. Okay, for that situation, what happens is that typically this is how your elastic curve might look like, depending on what load you have, right? So if the elastic curve looks like this, what it means is, why should I type this over here? This should rather be here. Okay. So, okay, great. Okay, good. All right. So here it means that you have slopes, right? So there'll be theta and theta. They'll mostly be the same. So it means that our theta here is not equal to 0, but our deflection here is 0. Okay. So to have a similar behavior, then it means that we'll have a beam with what we call an internal hinge. So this will give us an internal hinge. Okay. And for an internal hinge, your shear at an internal hinge is not equal to 0, but the moment at a hinge is 0. Okay. So then they satisfy the conditions we need to be able to find our moments and shear, which correlates to deflections and then the slope. So there are a few more in the text that I gave to you guys. Okay, I think I just have to add one, just the last bit, so that it looks complete. So what if the beam has an internal hinge, right? Instead of internal support. So an internal hinge, right? So in internal hinge, it means that this is what we have. Oops. Okay. Now when you apply the load, typically this is how the bending looks like. So like it kind of like bends into two, like downwards like that. So you have uh, the deflection, and also you have the slopes. Okay. So that it means that both deflections and the delta and the slopes are not equal to 0. Okay. So it means that you can also have, that means that the conjugate will be an internal support. Okay. So for that internal support, both V and then M are not equal to 0. Okay. So let's look at some examples of how to convert from a real beam to a conjugate beam, because that's one of the key things we need to do. All right. So let's say if I have, so again, under this whole real beam and conjugate beam thing, let me just continue like that. Okay. So if I have a prop like a simply supported beam, okay. So this is a real beam. All right. To convert into the conjugate beam, it ends up being the same thing. Okay. Because if we go back, we will see that when the support are at the ends and then they are either roller or pin, they do not change when we convert them to the conjugate beam types. Okay. If you have a cantilever whereby the fixed end is on the left, then it means that I'll end up with a cantilever whereby it must it more or less become a mirror copy of the other. Okay, because if it's fixed in the real beam, it becomes a free end in the conjugate beam. And where it is a free end in the real beam, it becomes a conjugate. It becomes a fixed end in the conjugate beam. Okay. And let's look at some more things, one or two more examples. So let's say I have another beam arrangement this way. So I have a pin support at the end and then a roller somewhere at mid-span or somewhere in between, okay, on the span. So we know that this will remain the same because I have here what you call an internal support. An internal support, it becomes an internal hinge. Okay. And then this end here is a free end, so it becomes a fixed end. Okay. So this is the transfer from real beam to conjugate beam. Okay. There are many more examples. Let me just do one more, then I think we should be good. So let's say I have this pretty huge structure. So there's a fixed end, there's an internal support, there's also an internal hinge, and then there's also a pin at the end. So let me just label them so that it becomes easy. So this is A, B, C, and D. So I can draw the same thing, label A, B, C, and D. Yeah, I can make them prime because of the fact that it is a conjugate. I mean, like it's an imaginary or not a real beam, right? So my support here will be free. B will become an internal hinge. C becomes an internal support, and D remains the way it was. So that's the idea of what a conjugate beam in terms of trying to convert from a real beam to a conjugate beam looks like. So before we solve any question, let's just go through the procedure of how to analyze these things. So the procedure for analysis, we can find the same information in the Hibla. All right. So the procedure for analysis is that if you have so the following procedure provides a method that may be used to determine the displacement and slope at a point on the elastic curve of a beam using the conjugate beam method. So the first thing we need to look at is first to draw the conjugate beam for the real beam, okay? Typically, or all the time, the conjugate beam has the same length as that of the real beam, all right? And then the table 8.2, it's the book is mentioned, it's pretty much what I have done in this table. So from the book, this would be table 8.2 from Hibla. I think hopefully I got the spelling right. All right, so from that table, that's what it means. Okay, so it should have the same length as and also has the same corresponding supports. Okay, so that's I gave some examples in this space right here. Okay, so looking at all these different beams, okay, because if you don't get your conjugate beam right, it doesn't matter what load you put on it. Right? It means that you might not end up with the right answer. Okay. So once we are able to define the conjugate beam, it gives us a rule of thumb that says that if the real support allows a slope, then the conjugate beam must develop a shear. Okay, we've gone through that just now. And also, if the real support allows a displacement, the conjugate beam support must also develop a moment. Okay, so that's it. Right. So once we draw our conjugate beam, oops. So when we draw the conjugate beam, assuming let's say I have this as my conjugate beam, maybe something like this, just for the fun of it, which means that my real beam used to be something like this. So this is the real beam, and this is a conjugate beam. Okay. So once you've drawn the conjugate beam having the same length as the real beam, the next thing to do is that you load the conjugate beam with the real beam's M over EI diagram. So when you find the bending moment diagram, depending on how the loading is, all right? So if this gives you maybe this bending moment diagram, maybe something like this. Okay, this is a bending moment diagram, for example. We have to come and put this bending moment diagram, assume it's a positive bending moment diagram. We need to come and put this bending moment diagram on the conjugate beam as a load. Okay, so we call this the M over EI diagram. Okay, so if maybe the load of the original beam was like this, and this gave us the bending moment diagram, then we take this bending moment diagram, divide it by the corresponding EI, and place the bending moment diagram as we've drawn it onto the conjugate beam, and that becomes the new load. Right? So we load the conjugate beam with the M over EI diagram. This loading is assumed to be distributed over the conjugate beam, and a few things to note. If our bending moment diagram is positive, like in my case is positive like this, then it means that the loading directions on the conjugate beam should be upwards. Okay. If, for example, we had a case whereby our bending moment diagram was, let's say, negative, then it means that, so if negative, then it means that our conjugate beam would have had something like this. So we can actually draw the negative. So this becomes our load on it, and this load moves downwards. Okay, so for a rule of thumb, whichever way you draw your bending moment diagram, you place it as a test on the conjugate beam. And then we know that our bending moment diagram, if the diagram is above the zero, it's positive. If it's below the zero, it's negative. And then we draw them as, or we place them as they are on the conjugate beam. Okay. Then based on that, we assume that the directions of the load should be moving away from the beam. Okay, so if it's positive, it's moving away from the beam. If it's negative, it's also moving away from the beam. It makes things easier for us, all right? So in other words, the loading is always acting away from the beam. Okay, so to make things easier, anytime we want to find the shear force, and then the bending moment on the conjugate beam. So all of this is on the conjugate beam. We assume that the unknown shear force is acting downwards, and then the bending moment is acting in the what's the name? In the counterclockwise direction. Okay. Normally, if you're moving from left to right. Okay. So that's the direction we go with. So if you assume that your shear force is acting downwards, let's say if I want to find a shear at a particular point, let's say D, then I assume D is acting downwards. So let's say V, or let me call this point B. So VB prime. If it's acting downwards, then it means that like we assume it's acting downwards. And if we get a positive value, if it's positive, then it means that our slope is counterclockwise. So if our shear force at any point is positive, then our slope is counterclockwise. Then if our moment is also positive, then our displacement is also upwards. So let's look at an example so that at least I don't have to go through talking more about this without any calculations to look at. All right, so let's look at an example. This is A and this is B. Okay. And then it says we should find theta B and delta B. Okay. We have already established these already, I think. Let me just see if we have that information from previous calculations. We should. Okay, so we have it. Theta base minus PL cube over 3EI. All right, so I'm going to pick that information. And then, so did we find theta C? Theta, so delta B is minus P3 cube over 3EI. Oh, we didn't find the other one. Okay, that's fine. I thought we did. Okay, anyways. So from the moment area method approach, we know that, so this is on the side, we know that delta B is equal to minus P PL cube over 3EI. And I think theta B is equal to PL squared over 2EI, I think. I'm not too sure, but I think that should be it. Okay. I think they should be negative also, but that's fine. So we have to use a conjugate beam method. So let's first draw. So we have an idea of our elastic curve. Okay. So I'm just drawing an elastic curve. Here, the elastic curve is not too critical. It's most critical with the moment area method, but not too critical with the conjugate beam. So I have my beam, and then my curve looks like this. Okay, so I have my delta B, then also have my, if I draw the tangent, theta B. Okay, all right. Now let's draw a bending moment diagram. So draw bending moment diagram. And this is why I was saying there at that time that at this point, I'm not expecting you to be solving the moment diagram from first principle, right? Where you find support reactions and find all of that and find the moment at point A, 1 meter, 2 meter. No, that is for basic structures. At this point, I'm expecting that we should easily know how to find moments without too much stress. Okay. So here, this is how the bending moment looks like. Okay. With it's a negative moment with the maximum value being PL over here. Okay. All right. Then the next thing is to formulate the conjugate beam. Okay. So this is a real beam. There's a real beam. So our conjugate beams look like this. So this is a conjugate beam. Okay. So we have our conjugate beam done. The next thing is to load the conjugate beam with the M over EI diagram. Okay. So I come back here, I take my conjugate beam as I've drawn it on the side, then I place the moment diagram as a load. So the moment diagram as a load will look like this. Okay. So because it's negative, I just pick it as it is and I just place it exactly the way it's supposed to look like. And from my procedure, I'm told that the loading is always acting away from the beam to make it easier. So I assume that the direction of my load, because now this becomes a new load, right? So this new load acts away from the beam. So this becomes my M over EI diagram. But here we know what our M is. Our M is what? PL. So PL over EI. Okay. So it's like I now have a new beam to design or to find the reactions for. Okay. So here, because it's a conjugate beam, I can name here A prime and name here B prime so that at least it separates the real beam from the conjugate beam. Okay. Now solve for the conjugate beam. Okay. And then we know that theta B in the real beam is the same as the shear force in the conjugate beam. Then delta B is the same as the bending moment or the moment in the conjugate beam. All right. So once we have established this, I can now redraw let me just make a copy of it. Okay. So I just take this It means that I have these reactions. So here, I assume that my VB is going downwards, okay? And then my moment is acting in the anti-clockwise direction. So let's say MB prime, okay? So if you are summing vertical forces, which is equal to 0, so we have a triangular load, which is a varying distributed load, right? So it means that this here, you can decide that okay, all downward forces are either positive or negative. It's entirely up to you. But let me make it all negative so that it's easy for our minds to agree with whatever is happening. So here I have so it means that minus VB prime minus this area. Okay, so the area is what? Half base. The base here is L. So half base, which is L, times a height of PL over EI. All right, so this is equal to 0. So it means that VB prime is equal to minus PL squared over 2EI. Okay, so you can see that there's a negative in front. This negative indicates that the negative indicates that the slope is clockwise. Okay. Clockwise in the sense that if you go back to my curve, then it means that the slope is measured in this direction. It's measured in the clockwise direction. That's all there is to it. Okay. So I think, as I mentioned, that there'll be negative in front of this. So we can see that our answer is the same. All right. Whatever we got for the moment area method is the same for the conjugate B method. Okay. The next thing is to find the moment MB. So let's say summation of moment at B prime equals 0. So MB prime plus the moment due to the triangular load. Okay. And the moment is simply the area times the perpendicular distance between the centroid of the triangle to B prime. So that will give us half. So I'm putting together the area now, which is the load. Then the centroid will be somewhere here. So this becomes my X bar. Okay. So that will give us times 2/3 of L. Okay. And all of this will be equal to 0. So MB prime plus you get PL cubed over 3EI equals 0. And this means that our MB prime is equal to minus PL cubed over 3EI. And this is the same as the delta at B. This one, everything here is the same as the delta, the theta at B. All right. So this is an example of the conjugate beam method. Okay, so I'll solve one more example, and then we can there'll be any assignments on this yet. I think I'll give the assignments next week, and then at least by then we should. I'm sure if we meet next week, we will solve some more questions too on the conjugate beam method, right? So here I have. Let's look at maybe example 2. So I have an example where here I have actual values. Okay. So I have an 8 kilonewton load. And then this is 9 meters, 3 meters. Okay, so I have this points A, B, and C. And I'm to determine so determine the slope at A, slope at B, and then deflection at C. So again, I go through all of these again. So I can draw the Benjamin diagram. And the Benjamin diagram, so so let me say solution. So this is the bending moment diagram. Okay, so the maximum value here is PAB over L, which is the same as 8 times 9 times 3 over 12. Okay. And this will give us 18 kilonewtons meter. I mean, these are equations we can use to help us to solve our problem. All right. So this becomes the bending moment diagram. So this is the first one. And the second one, I draw my conjugate beam. So my conjugate beam will look pretty much the same because that's, let me change the color so that it looks like something different. So they are the same. Okay. Then I load my conjugate beam with my bending moment diagram. Okay. So since this is a positive bending moment, my loads are acting upwards. And then the value here is 18 over EI. We have these various lengths right here. And this is 9 meters and this is 3 meters. So the points now, let's say, I can just say A prime, C prime, and then B prime. Okay, so now I have my conjugate beam. So this is the conjugate beam. Okay. So once I have the conjugate beam, if I find, it means that if I find my shear force, if I find VB prime is the same as theta B, if I find VA prime is the same as theta A, if I find the moment at C prime is the same as delta C. So that's the beauty of the conjugate beam method. It's, I think, in my opinion, it's an easier approach than the moment area method. Okay. All right, so let's look at how to solve this problem. Okay. So I assume that all my support reactions are acting downwards. Okay, that's the assumptions we make. And then, so I have to find VA prime and then VB prime. All right, so we can say, let's say summation of, sorry, let's start with summation of vertical forces first. So we equal to 0. So we know that VA prime plus VB prime will equal to the area of this load. Okay. You can easily find an area, and it depends on you. Sometimes you can break them into two. So I'll do that. Okay. I would have this section here and then this section there. Okay. It doesn't really change anything. So I'll end up with half times a base of 9 times a height of 18 over EI, then plus half times a base of 3 times a height of 18 over EI. You can combine them, it wouldn't change anything. Okay. So if we go by this approach, I didn't compute it for whatever reason, so let me just do it here. So 18 times 9 divided by 2. So I get 81 over EI plus, this is 18 times, or 9 times 3. So I get 27 over EI. Okay. So that will give us what? 108 over EI. Okay. So let's say we take moment about B or B prime. So summation of moment about B prime to be equal to 0. Okay. So we have 12 VA prime, which will be equal to, so now we can look at the first triangle. So that's where with the first triangle. And then we know that the area of that one is what? Half times a base of 9 times 18 over EI. So this becomes the area. And then the corresponding moment becomes 1/3 of 9. So 9 over 3 plus this extra distance of 3. Okay. So this is the first one. Then the second one, we have this small portion here, which will be again half of 3 times a height of 18 over EI times from the centroid to the point B prime will be 2/3 of 3, not 6. So this becomes also another 1. So from here, you can easily find your answers. If you do this, you get 486 over EI plus this one will give us 54 over EI, and that'll give us 540 over EI. So we have 12 VA is equal to all of that. So it means that VA prime will be equal to 540 over EI divided by 12, and that'll give us 45 over EI. And then VB prime will be equal to 108 minus 45. Okay. So that'll give us 63 over EI. Okay. So it means that our theta A, so from here, it means that our theta A is 45 over EI. Okay. And our theta B is 63 over EI. And since they are both positive, then it means that the angle is measured counterclockwise or anti-clockwise. Okay. In both cases. Okay. All right. Now, if you want to find theta delta C, we have about some 10 minutes. Let's wrap it up. So if you want to find delta C, okay, which is at this point, you can either use from left to right or from right to left. It's entirely up to you. But let's do from left to right. So I already have this diagram here. To have something like this, right? So this is what we have initially. Okay. And then we have all our reactions. So I can cut a section at where C acts. Okay. So that I can either end up with a left-hand side or a right-hand side. Okay, it's up to us. So let's go with the left-hand side. Okay. So if I go with the left-hand side, let me use this option. So where is that? Okay. So if I go with the left-hand side, this is what I'll end up with. Okay, so I've cut that section away. So it means that anytime you cut a section on a beam, you introduce the internal forces, right? So there'll be an MA, or in this case, MC prime. There'll be a corresponding VC prime, and also an HC prime. But because in this case, the AC prime here goes to 0, so we don't really bring it. But this is what happens, okay? Our goal is to find the MC prime. Okay. So to find MC prime, since we already know what VA prime is, you can say, let's say, summation of moments at C prime equals 0. So we have VA prime times the distance between A and C, which is 9 meters. Okay. And then that will cause an anti-clockwise moment about C, then plus MC prime. They are all moving in the same direction. So this is the direction of the VA, and is the direction of the MC. Okay. Then minus the moment due to the triangular load. So again, it's half times a base of 9 times a height of 18 over EI. So the height here is 18 over EI. Okay. So 18 over EI. And then the moment arm will be from the centroid here all the way to this point, and that'll give us L over 3, or 1/3 of the length. So it becomes 9 over 3, and all of this is equal to 0. Okay, but we know VA to be 45, right? So I can write that, okay, 45 times 9 plus MC prime minus all of this, and that should give us 9 times 6 times 9 times 3 times 9. So minus 243 over EI equals 0. So our MC prime would be equal to 243. This also over EI. So 243 over EI minus 45 times 9 will give us 405. So minus 405 over EI. So we get what? Minus 162 over EI. Okay. So that's our MC. So if we know that if we have E and we also have I, we can put them into the equation and find the actual deflection. All right. So the bracket negative which means that the displacement acts downwards. Yep, so that's it. So that's it for the conjugate beam approach. All right. Any questions?
No, sir.
Okay. So if we don't have any Let's just go through the notes, go through some of the two examples, and then if you have any questions, you can always get in touch with me, and then we can work something around it. So I think let me just go through what we have for today. So we looked at the conjugate B method. We explained that it is an example of the geometric method, the same as that of the moment area. We looked at the correlation between loadings and then deformations, and then we're able to develop two theorems based on that. And then from there, we looked at what we call the conjugate beam. Okay. Then we are able to analyze structures based on the conjugate beam approach, whereby deflections in the conjugate beam or shear in the conjugate beam will be equal to the slope in the real beam, and then bending moment or bending in the conjugate beam will be equal to or will be the same as the displacement in the real beam, right? So we solved two examples, a cantilever and then that of a simply supported beam, to appreciate the procedure involved in arriving at expected results, right? All right, so let's end here today, and then we'll enjoy and then let's enjoy the rest of our weekend. So welcome to today's lecture, I think lecture 5. Last week, so there's a recap of what we looked at last week. So I think last week we introduced the conjugate beam method. We explained that the conjugate beam method is a geometric method, just like the moment area method. So they both use the geometry of the bending moment diagram to calculate the slopes and the deflections at various points on the structure. All right. The key difference between the moment area method and then the conjugate beam method has to do with the fact that with the moment area method, the elastic curve is very critical in the analysis process. All right. Whereas with the conjugate beam method, we try to create, should I say, an imaginary beam, or in this case, we call it a conjugate beam, a beam that is opposite to that of the real beam, in a sense that we're creating a beam whereby when we calculate the let's say the shear in a conjugate beam, we can relate that shear information to the slope and the real beam. Then also when we calculate the moment or the bending moment at various sections in the conjugate beam, we can also relate that information to the real beam. Okay, so we went through the process of how to convert the real beam first into a conjugate beam. Okay, so the key thing was to go through the supports, understand how the supports behave both in the real beam and also in the conjugate beam. All right. So in a real beam, if you have a pin support, okay, a pin support, we know that a pin support has two support reactions. So let me just do this so that CENG 255. Okay, great. Oops, lecture 4, right? Okay, I know lecture 5. Okay. So we are looking at a recap. Hope everything is showing, everything is recording. All right. So we're looking at a recap um, of lecture 4. Okay. So I was saying that if we have on the real beam, so these are the supports, right? So we have the HA if the support is um, support A. Okay. And then there's an elastic curve or the bending behavior. All right. So here we can see this rotation, theta A. And we have this rotation because a pin support, has no resistance to rotation. All right. So typically pin support has no resistance to rotation. So it means that it will rotate. Okay. So if you look at the hinge of a door, the because of the presence of the hinge, the door cannot move upward. It cannot be pulled towards you or pushed towards the frame because it has resistance against horizontal motion. But you can open and close the door. And the reason you can open and close the door is because the hinge cannot resist rotational motion. All right, so the door is able to rotate towards you and then rotates back into place. All right, so that rotation definitely will lead to a slope or an angle being formed. All right, so that angle is theta A. So because it is not able to move vertically, or where VA is 0, then it also implies that the deflection, at that particular point, delta A, would also be 0. So that's the idea. Rotation at A will not be equal to 0. Okay, so we don't know what that value is. Okay, so we also need to design a conjugate or a beam, which in this case we call the conjugate beam. So all of this is for the real beam. Also need to design a conjugate beam so that we could end up with a similar or the same representation as this is. Okay, so if I'm to draw another beam, okay, because we know that from our previous lecture, we know that the deflection in the real beam, we can relate it to the bending moment in the conjugate beam. So let me say RB for real beam and then CB for conjugate beam. We know that, okay? They also know that the slope at any point, so let me just take away the AA. The slope at any point is the same as finding the shear at the conjugate beam if you're comparing the two. All right. So again, we also need to devise a case whereby, I don't need this one, whereby this reaction VA and then the moment MA. So let me say MA prime and VA prime because it's a conjugate beam. All right. So if you take a pin support, again, a pin support if you're looking at its in terms of its forces, all right. This one is the first one, the real beam is looking at its compatibility, right? We are looking at equations of slopes and deflections, but in the conjugate beam, we are looking at equations of forces, which are um, shear and bending, all right? So here, for a pin support, we always end up with a reaction, all right? but the moment at a pin support, MA, is 0. All right, because a pin support has no resistance to rotation. So we can compare the two, and then we say, okay, the moment which is 0 is the same as the deflection which is 0 in the real beam. All right. And then the shear which has a value will be the same as the rotation or the slope in A, which also has a value. So that's the idea of the conjugate beam. All right. And to explain again, if you look at a fixed support, okay, a fixed support, this is the so this is the elastic curve um, or the deflected shape. Okay. So if you look at it closely, it's straight up to a point before it starts bending. All right. So what this indicates is that there's no rotation at this point. So let me call this point A again. There's no rotation at A. All right. So because there's no rotation at A, so rotation at A equals 0. And again, because it's a fixed support, A will not undergo any deflection. All right. So now we need to find a beam which can give us the case whereby the shear at that point and then the moment at that point will be 0. Okay. And the only beam that we can think of, so if this is fixed, again, this is the real beam, is to have a beam whereby there's no support. Because once there's no support, the shear force there, or oops, if there's no support, then pretty much all the reactions at that point should be 0. All right, so that means that here too, our shear VA prime will be 0, and then MA prime would also be 0. All right, and then these two we can relate the two. So that's one thing to take note of, all right, when dealing with such or going through the whole support condition. So again, if you go back to the previous lecture, we went through all of these processes, all right, and I explained that I think this can be found in table 8.2 or 8-2 in the structural analysis book by R.C. Hibler. Okay. So we give ourselves different examples here and there to be able to appreciate what goes into these supports here and there. And I also mentioned that because of that, we can derive two theorems. All right. The first theorem states that when comparing the slope or the slope in a real beam and then the shear in a conjugate beam, we can write a theorem that states that the slope at a point in a real beam is numerically equal to the shear at the corresponding point in a conjugate beam. In the same way, we can also have the second theorem, which also states that the displacement, okay, or deflection of a point in a real beam is also equal to the moment or the bending moment at the corresponding point in a conjugate beam. It's a fair enough or a pretty straightforward theorem or theorems. All right, so I think we looked at the analysis process on how to solve some of these problems. I think we mentioned that the first thing is to you can draw your bending moment diagram from the real beam. Then from there, you create your conjugate beam. All right. Now, when you create the conjugate beam, you load the conjugate beam with the bending moment from the previous calculations. Okay, so here it's a specialized type of bending moment, which we call the M over AI diagram, which simply means that dividing the moment by the flexural rigidity. All right. So when you load the M over EI diagram, so now you have a new beam, a conjugate beam with a new load. All right. Where the load used to be the bending moment from the real beam. Okay. A few things to take note of when doing such things is to make sure that we get our directions right. So we come up with this convention that's at all points, the load on the conjugate beam should be moving away from the beam. Okay. So in that sense,
So a question, please.
yeah, go ahead, sir.
Please, can you explain further what you mean by a load on the conjugate beam should be moving away from the beam?
Okay, I was just about to. All right.
Yes. Okay.
So let's say we have a beam. All right, just so this is a real beam, okay? Then we had its load, whatever the loads might be. Okay. You also have its support conditions and all that. Okay. So this is a load. Okay. Then from the load, this becomes our bending moment diagram. Let me just show the so this is for the real beam. Okay. Then this becomes, let's say this becomes maybe our bending moment diagram. I'm just drawing something, okay? So this is a positive moment, okay? So bending moment diagram, great. Then the next thing we look at is the conjugate beam, okay? So what happens is that we take the beam itself, not the beam with just only the beam, okay? And then convert the real beam to the conjugate beam. In this case, they will be the same, so no problem, right? So we end up with something like this. Okay. Now, our load on the conjugate beam will be the bending moment diagram from the real beam. So we just take this right here and then come and dump it as our new load. So we'll end up with something like this. Okay, just like what you had. I mean, they're a little bit different, but we get the idea. Great. Okay. So since this is positive, we place it on the positive side, okay, on the positive face, right? So this is positive, this is negative, okay? Then we, once the bending moment diagram becomes a load, we need to indicate what direction the load would go in, right? Before we can find reactions. So here we assume that since it's on a positive face, we place the moment on a positive face also, and then we put our loads going away. All right. So this is for in a case whereby everything is positive. Okay. Um, all right. And then we also assume that our support reactions are moving downwards. So this for positive, and also assume support reactions, and this only for the conjugate section. I assume support reactions are downwards. Right. It makes so like everything is opposite, right? That's the idea. Okay, conjugate opposite in a way. Then if you have a case whereby I'm done with this section. Let's say we have another, so this is case 1. Not case 2, case 1. Then we have another case whereby, again, let's say similar loading, whatever the loads might be or whatever, so that we end up with a negative bending moment. Okay. Let me make sure they are the same so that it doesn't confuse anybody. And let's say we get a negative bending moment. All right. So this is for the real beam. Okay. So again, we have our conjugate beam. So with the conjugate beam, what happens is that you load it. So the way the bending moment diagram has been drawn on the real beam, we just place it in the same direction, the same position, okay? So it will be downwards this way. All right. Then the forces or the direction of the load is away from the beam, right? So in the two cases, which is this case 1 here and case 2 over here, you can see that both of them have their loads moving away from the conjugate beam. Okay, so that's what I mean by convention, let your loads move away from the conjugate beam. All right. So we are working with the fact that we position the loads or the bending moment as loads on the conjugate beam in the position they were in the real beam, and that indicates that all the directions of the load is moving away from the beam. Okay. So again, so this will be so let me call this a negative. Okay. Then so again, we also assume that our reactions here are downwards. So the same vein as this right here. And then you solve for whichever points of interest that we have. All right. So we went through, I'll go through some of the examples we went through last so that we appreciate what happened. So I think I had about how many examples? 1, 2. Okay, went through only 2 examples. Okay, so I'll go through some of the examples again. Then at least the example 2. So I'm recapping. Recap example 2. Okay. So with example 2 last week, we had a beam, a simply supported beam with a ruler at point A and then a pin support at point C. Then we had, I think, an 8 kilonewton load. Okay. Then this was 9 meters and 3 meters. Great. Okay. And I think we tried solving for the so we're to solve for the slope at A, slope at B, and then the deflection at C. So this is point C. All right. So these were our calculations. All right. So in terms of the solutions, so we start with step A. Draw your bending moment diagram. I think I did explain that at this point, I'm expecting you guys to quickly sketch it without going through trying to find reaction at A, reaction at B, and finding moment at different sections before we draw it, okay? Because the goal here is not to draw the bending moment of the real beam. The goal is to use that information to come up with slopes and displacement. So we cannot spend our entire time trying to figure out how to draw the bending moment for the real beam. And as such, we need to up our game on bending moment diagram drawings. Again, I've mentioned that what's the name? I've mentioned that we could have more P and TA sessions and all that. I'm making some arrangement as to that. I think I'll get you guys feedback hopefully by Monday to see how you can have some PA sessions. All right. But for now, when you need any issues in terms of trying to figure out how to draw a movement diagram, I suggest you get in touch with me quickly, because everything we are doing in this course and even next semester is all about bending moments. All right. So a good grasp on how to do it will go a long way to help you understand the course or appreciate the course a bit better. Okay. So here, if I draw my bending moment diagram, this is how it looks like. Okay. This value here would be 18 kilonewton meter. And I got that using the equation PAB over L. The P is the low, which is 8. The A is the distance on the left. Okay, so, and now it's 9. B is the distance on the right of P, which is 3. And then L is the entire length of the beam, which is 12. Okay. This equation only works for this configuration. Any other configuration and equation might be a bit different. Okay. So it's not a fit for all kind of equation. All right. So this is a positive bending moment. Okay. Now we create our conjugate beam. Oops. So here the conjugate beam is fairly straightforward. It's the same as the original beam, so we don't really change anything. But we maintain it because whatever we have in a real beam will be the same in a conjugate beam in this case. Okay. So once we create the conjugate beam, the next thing is to load the conjugate beam with what we call the M over EI diagram. All right. So the M over the M here is the moment. So the moment over the EI diagram. So simply dividing through by EI. Okay. So we load. So I just put this right on top. So whatever I had here in this space, I just bring it back here. That's all. All right. And since it's positive, I place it on the top. Then assume that the directions are upwards. Okay, great. So nothing really changes. 9 meters, 3 meters. Now have 18 over EI. Okay. So here's 18 over EI for the topmost value. All right. And I'm to find, so now if this is, so if here was A, let me call this A prime and B prime, just to indicate that they are in the conjugate mode, right? So it means that if I find V A prime, it relates to the same as finding theta A. If I find V B prime, the same as finding theta B. And then if I find the moment at C, or the bending moment at C prime, then that will be the same as finding the deflection. Oops, the deflection at C. And that's the idea. All right. Okay. So I have these support conditions. So this is VA prime and VB prime. Okay, so now let's solve for this. So summation of forces in the vertical direction is 0. So I'm pretty sure you guys did varying distributed loads, right? Or at least we've mentioned that. Okay. If you have a beam with a triangular load or a trapezoidal load on it, it is called a varying distributed load. So a typical example is this. Okay. So here, summation of vertical forces, upward is equal to downward, right? So I can say that VA prime plus VB prime, since they're in the downward direction, this will be equal to the triangular load. Okay. Now it's just straightforward to just sum everything up or divide that into 2. Okay. to make things easier, I'm going to divide mine into two. So I have two triangles. So one on the left. So this is my first triangle. Then I have another triangle on the side. Okay. So I have two triangles. Let me also color this one. All right. So the red one on the left, the area, anytime you're finding load of a distributed load, you have to find the area of that load, okay? So it's triangle, so it's half base times height. So half, the base is 9, the height is 18. So it's 18 over EI. All right. Well, let me do it this way. Half of 9 times 18 over EI. This makes much more sense. All right. Then plus the right side, again, the half base of 3 times the height of 18 over EI. And then when we sum all of these up, okay, that should give us 108 over EI. Okay. Now we need to find one of these reactions. So let's take summation of moment at B prime to be equal to 0. So we are taking moment about the far end on the right. Okay. So that means that here again, pay attention to directions of rotations, right? So V will cause a counterclockwise rotation or VA prime will cause a counterclockwise rotation about B. All right. So here becomes 12 VA prime. And that should be equal to, then we can again look at the individual or the two triangles. All right. So for a triangle on the left side, we have the area, which will give us the load. So I'm just writing everything that I wrote earlier. So this is simply the load. Okay. And moment is what? Load times what? The moment arm, right? Okay. So the moment arm will be from the centroid of the triangular load to point B. Okay. So that would give us half of 9, sorry, 1/3 of 9, because it's acting somewhere here, right? So 1/3 of 9 all the way to B prime. Okay. So 1/3 of 9 plus 3. Okay. So this is one set. Okay. Then the right-hand side, again, the area is the same, nothing changes. So this is the reason why I divided the area into 2 when solving for or when summing up forces, because it also helps me when dealing with the moments. Okay. So again, here is the load. Now times the moment arm. So the moment arm here will be 2/3 of 3 meters. Okay. Then we can simplify this equation or this set of equations, and this will give us I think this is 486 over EI plus 54 over EI, and this will give us 540 over EI. So if the 12 goes to divide, then it means that our VA prime is 45 over EI. Okay. Then our VB will simply be this 108 minus VA, right? So VB will also be 63 over EI. All right. So that's so one thing to note is that since our displacement, sorry, our shear forces, or VA prime and VB prime, are positive, it also indicates that the slope is counterclockwise. All right. So pretty much this is equal to theta A, and then this is equal to theta B. Okay. So that's all that it means. All right. So if we know the value of EI, then it means that these will be in radians. Okay. They'll all be in radians. So if E is, let's say, 200 GPA, and maybe I is maybe some 10 times 10 exponent 6 mm4 or something like that, we could easily determine our slope in terms of the actual value. Okay. So both are counterclockwise. Now we need to find the moment at C. Okay, because the moment at C is what we need, or at C prime, so that we can find the deflection at C. So anywhere we want to find moment, we cut at that section. Okay, so that's the idea. We cut at that section. So let's say, so again, this is our loading configuration for the conjugate beam. And then we have these these directions for the loads. Okay. All right. So since our interest is at point C, okay, so I'll cut the section into two along C. So I have a left-hand side and then a right-hand side. Whichever one you would want to use for your calculations is fine. And then we know that anytime you cut a section, at any point along the beam, you would introduce three unknowns, right? Per the three equilibrium equations. So we have a moment, a shear, and then a horizontal or an axial force. Okay. So let's deal with the left-hand side. So with our left-hand side, we have this behavior. All right. So here we have these unknown reactions. And then we also have this horizontal. Okay. I'm bringing it here because it's important to note that there's always a horizontal component. All right. Just that in this case, this goes to 0, so we can ignore it, but that's what we have happens. All right. So our goal is to find MC prime. Okay. So to find MC prime, we take summation of moments at C. So we take summation of moments at C prime to be equal to 0. All right. So we know our VA. We're given the VA prime as 45 over EI that we have already solved for. All right. So if summation at C prime is the same, then it means that we have VA prime times 9 meters. The distance here is 9 meters minus the UDL, sorry, the VDL. And then the area of the VDL is half times half base times the height of 18 over EI. So yes, it's still 18 over EI. And then from the center of the UDL, of the VDL, sorry, to point C will be 1/3 of 9. Okay. So this is 4. And then plus the MC prime, and all of this is equal to 0. Okay. The MC prime is moving in the same direction as the load VA prime. The reason why we have the MC prime, even though we are finding moments about C, is because MC is a point moment. All right. So because it's a point moment, it cannot be zero in the sense that, or the reason why VC prime is zero is because usually VC prime is zero because if you're finding moment at C, you need to multiply VC by the moment arm. And because VC is occurring at the same point as point C, the moment arm is zero. And that's how come the moment due to VC prime is also zero. Okay. But MC prime is a point moment. So it doesn't need a moment arm. So that point moment will still be there. And that's how come it's part of this equation. Okay. I think I saw something like that in one of your assignments or so. Okay. Again, the solutions for the first assignment have also been posted. If for some reason you don't understand anything, um, excuse me, you could always get back to me on it and then we can meet and then discuss further. All right. Okay. So here we need to find MC prime. So we know what V is. So simply 45 over EI times 9. And I think this whole thing becomes minus 243 over EI plus MC prime equals 0. All right, so here our MC prime is simply 243 over EI minus, I think this is 405, right? Over EI. And that should give us minus 162 over EI. So our MC prime is equal to negative 162 over EI. And then what that indicates is that if your, so sorry, let me just do this. So this is equal to delta at C, all right? It looks unassuming. Okay, so delta at C, so this is delta at C. And because it's negative, it also indicates that our displacement is downwards. It means that C is bending downwards, or the displacement due to C, our point C, is a downward displacement. Okay. All right, so let's look at some more examples. Today we'll try and solve some more examples just to help us to appreciate what goes on. So I think these steps should help us in terms of determining the slopes and deflections at various points. Okay. Okay, so let's look at so let me call this example 3. So okay, great. So that's how we have a cantilever, and then we have the load halfway. So this is 20 kilonewtons, and then 5 meters, 5 meters. And now these points A, B, and C. All right. And so here we have E. Okay. So here we're giving E to be what am I? E was given as 200 GP. Okay. And then I was giving us 475 times 10 exponent 3 mm 4. Okay, and then we have to determine the deflection. So we should determine the slope at C and then deflection at C. All right. So again, we draw a bending moment diagram. Okay. So a bending moment diagram. So this is P times L, where the L is the distance between where the load is and then the point of interest. So between A and B. So this becomes, so let me say P times maybe L1. Okay, so that it doesn't, and so this is simply 20 minus 20 times 5. Oops. So this will give us 100. So this is 100. Right, so minus 100. Okay, so it means that our bending moment is a negative bending moment. Okay. So once we have this, we load it on the M over AI. I mean, we load this on the conjugate beam. Okay. So our conjugate beam, we know that in a conjugate beam, if A is fixed, this is A prime, B prime, and C prime. If A is fixed in the real beam, it becomes a free end in the conjugate beam. And then if the support is a free support in the real beam, it becomes a fixed support in the conjugate beam. So in simple terms, A prime is free, and then C prime will have a fixed support. Okay. So it's like flipping it. All right. But I don't want you to assume that it is just merely flipping the beam to get the same thing as in the conjugate beam. All right, it's not merely flipping it. It's just that it follows a set of principles that we have already stated last week. Okay. So here means that I can find my VC prime and then find my MC prime. If I find that MC prime is the same as delta C, and then VC prime is the same as theta C. Okay. So once I have my conjugate beam, then I load the conjugate beam with the M over AI diagram. Okay. So again, let me just draw my conjugate beam. Okay, and I place my load as it is. As it is right here. Okay. So now my load is moving away. Okay. There is no support at A anymore because now I'm looking at the conjugate beam. So it's 100 over EI. So once I have this in place, it means that I need to find these reactions, MC prime and VC prime. Okay. So to find MC prime, or let's start with VC prime. So we go with summation of forces in the y direction to be equal to 0. So it implies that VC prime minus, VC prime plus, because they're all in the same direction, right? So VC prime plus the area of the triangular load will be, half base times height. The base is the distance here, which is 5 meters. So 5 times the height of 100 over EI, and that should give us 0. So here our VC prime will be equal to, if we divide through, that'll give us minus 250 over EI. Okay. So what this indicates is that our slope is clockwise, all right? Because every time we get a negative value, it means that our slope is clockwise. It's gonna be a long day, all right? second. Do I have this right here? A second, okay. Where can I find this document? I'm looking for a document. Let me see if I can find it shortly. Shit. Oh, okay. Just bear with me for a few minutes. Let me pull something up. Okay, should be up and running shortly. Okay, I think we are good to go. Okay, all right. So I think we could let me just resume. Wait, what's happening to my screen? Okay. All right, I'm guessing you can see my screen now. All right, great. Okay. Yeah, so no, we know E, I think we're giving EI. So we can place them into our equations. So E was given as 200 GPa and I is 475 times 10 exponent 6. Is that what I had? 10 exponent 6, sorry. 10 exponent 6. All right. So we can put them into the equation here. And then we should end up with so here will give us minus 250. Our E is 200 GPa. So let's say 200 times 10 exponent 6. Okay. We are converting from GPa to kilonewtons, right? So that's kp. Okay. Then we have 475 times 10 exponent minus 6, I believe. Yeah. So once we put this into the equation, we should end up with a VC value of minus 0.00263 radians, or some books will just put it this way, minus 0.263 times 10 exponent minus 3 radius. I think, am I correct? Yeah, that's my calculator. Okay, so that it looks nicer. I mean, it's just a matter of using the engineering form so that it looks also, sorry, actually minus 2.63. All right, so that times 10 exponents minus 3 radians. Great, great. Okay, so once we have that in mind, then it means that, so this is supposed to be, this is a clockwise, okay, something like that. I mean, you don't need to put that into the brackets, right? Unless maybe I can find out, okay, in what direction is the is a deflection, or in what direction is the slope. All right, and that you should be able to state. Okay, now we need to find MC prime. To find MC prime, again, we could do summation of moment at C prime to be equal to 0. So we have so we can see that the moment MC prime and then the load will be in the same direction. All right. So we'll end up with MC prime plus the load, which is half of 5, times 100 over EI, which is the load. So again, this is our load, then times the moment arm. And then the moment arm will be 2/3 of 5 plus 5. All right, so all of this is equal to 0. Okay. So we can do that, find the, what's the name? So this is 250 plus, or 250 over EI times, I think, 8.33. Also will give us our MC prime. So it means that MC prime plus 1, I think 2083 over EI is equal to 0. Okay. So this indicates that our MC prime is equal to minus 2083 over EI. Okay. We know what EI is, so minus 2083 divided by 200 times 10 exponent 6, then times 475 times 10 exponent minus 6. And that will give us a value of minus 0.0219 meters, which can then be the same as minus 21.9 millimeters. Okay, so this is a downward deflection. Okay. So this is also one more example. There are a few others that we could use. Let's look at one additional case where it's a little bit different, that we can appreciate how the conjugate beam method works. Okay. So again, example. This will be our example 4. All right, so with example 4, to have a bit of everything, okay, so that we can appreciate what goes into it. So again, I have a beam, a simply supported beam, okay. One end is fixed, one end has a roller, and so to indicate how the beam looks like in real life, let me just draw the beam. Okay. So this is a beam in real life. There's a point load right at this edge here. There's a point load at the midpoint. There's a point load at the edge. Okay. So this is 30 kilonewton. This is 40. It's also 30. Okay. Then we have these dimensions. So yes, 4 meters, 2 meters, 2 meters, and then 4 meters. Okay. So we can see that this section here, so the beam on this point is thicker. It's thicker than the beam over here. Okay. So definitely, because they have different cross sections, it means that their moments of inertia would also be different. Okay. So let me name this point. Oops. This point A. And let me name this point C and B. Okay. Those are the key points that have interesting. So I can name here D and E. All right. So member DE, which is the pink shade shaded, has a different moment of inertia. Okay, and that will be so let me call it 540. So the oops. So this is equal to 540 times 10 exponent 6 and then 4. Then member AD and EB, they also have a different moment of inertia, which will be 270. So that's like half of E. The E remains the same because it's the same material. So E is giving us 200 GPa, which is typically the Young's modulus for steel. Okay. Now, great. We are to, what's the name? Find the deflection at C. Okay, so the question says find deflection at C. Oops. So find delta C. Okay. So here, first thing is draw the bending moment diagram. Okay. That's the key thing to do. All right. And we can easily find our reactions. This is a fairly straightforward approach. The reactions will be V will be 50 and then VB also be 50. All right. Because it's half of all the loads. Again, at this point, I'm expecting us to be able to easily calculate the reaction. So let me see section 1, draw the bending moment diagram. Okay. So I could take the beam in its simple mode this way, have these reactions on it. Okay. So this is 30, 40, 30. So I need to find VA and then find VB. All right. So VA plus VB will be equal to 100. Okay. And since this is a symmetrical system, it means that VA is the same as VB. Okay. Again, if you don't understand any of these things, I would humbly request that we schedule office hours or some meeting so that we could discuss this a bit further. All right. So based on that, my bending moment diagram will look like this right here. This is 50 kilonewtons. So this is A. I have A, D, C, E, and B. From A to D, the value is 200, I think, yeah. Then from D to C, let me just, okay, at least it looks a bit funny. So it takes the shape like that. So 200, this is 240, it's also 200. Okay. So it's like you have different sections, something like that. Okay, so this is your bending moment diagram. And it's a positive bending moment diagram. So this is bending moment diagram. The next thing is to draw your conjugate beam, right? So draw conjugate beam and then load the beam with the M over EI diagram. Okay. Here, the M over EI diagram will change. So this is a bending moment diagram. So let me say this is the M diagram. I'm trying to convert this into the M over EI diagram. Sometimes your students are interested. I just had a message from one of your mates saying that there's no Wi-Fi in the library, so he's not been able to join the class since morning. I don't know what to do about that one. Okay.
You should. Right. But sir, okay, all right.
When I hear these things, sometimes I'm a little bit surprised because it's either so now let's look at the conjugate beam. Let's look at what to do with it. Okay. Now our goal is to draw the M over EI diagram. Okay. We know that if you look at okay, no, let me just rather write the word. So let me write it here that draw the M over EI diagram. Okay, great. So I need to convert this into something that will give me an interesting idea. Okay. So we know that from A to D, our I is 540. And then from what was the name from D to E is from A to D, it is 270. Then from D to E is 540. And then from E to B is also 270. So I can find a relationship between these two here. So I can find, so I'm going to bring that down here. Forgive me for all this. All right. So let me say I of DE, right? It's 540 times 10 exponent 6 mm4. Okay. For now, I'll leave that out. And then we know that IAD, which is the same as IEB, it's 270 times 10 exponent 6. So we can see that 2IAD is the same as IDE. Okay. If I multiply the moment of inertia AD or EB times 2, I'll get the IDE, right? So if I don't know if I'm using the right color, but if IDE is equal to I, then this implies that no, okay. Rather, let me do it this way. If IAD is equal to I, then this implies that our IDE will be equal to 2I. Okay. So to make things easier. So I'll take you guys through first principles, explain everything, and then subsequent ones will just make it easier. All right. So this is what we have. Okay. So let me increase the size. So here we have 200. So our M over EI diagram. So we have this junction right here. Oops, different color. We have this junction over here. At this junction, we have 200, right? So 200 over, so this junction here, which is here, right? This place, right? This is our junction. So this junction is being shared by two beams with two different I values, right? That junction here is being shared by AD and also DC. Okay. So actually, what is happening here is that to exaggerate a little bit, let me just so here becomes 200 over IAD, and at the same time, it also becomes um 200. Oops, 200 over IDE. Okay, so that same point is being shared by two different beams. Here, this place, because on both sides is the same thing anyway. So here becomes 250 over IDE. Then here we have something similar to whatever we had before. Let me just make it look. So here it becomes 200. Again, it's being shared by, so at E, we have both IDE, and then we also have at the same point 200 over IEB. Okay. So that's what is going on over there again. So I could do it this way. So this is the M over EI diagram. So M over EI diagram. Okay. So let me just do some more math or some more magic, and let's see how things will show up. Okay. So I know that wherever I see IAD, so wherever oops, let me make sure. Okay. So wherever I see IAD, I can put in I. So here IAD is the same as IEB anyway. So they are both I. So whenever I see IAD or I see IEB, I can put in I to make things easier. And then wherever I see IDE, I can put in 2I. All right. So I'm just going to replace that over here for us to see. So my IAD is the same as IAB is the same as I. So let me just do it nicely. So this is I, this is also I. And wherever I see IDE, I write 2I. Okay. So 2I and 2I. Okay. So what this does is it helps us to appreciate a few things. Make a copy, paste on the right side. I think it should work. Okay, great. So that I don't have to. Yeah. So it means that here, this now, if you divide through by, if you divide 200 by 2, you get what, 100, right? So, um, so this one becomes 110 divided by I, and then this becomes 250 is what? 120. 250, sorry, what did I get? 250 or 240? Let me see. 240. So how come I keep writing 250? Sorry. So here's 240, not 250. Oops. 240, sorry. Correct all of them. This is 240. Okay. So here I get 120 over I. Okay. And then here too I get 100. Okay. So what this will do is that to represent the oops. Okay. So to represent the differences, it means that I'll end up with this situation. Again, make a copy of it. Okay. Normally, you not go through all of these processes. Okay, it's just that we appreciate what is going on. So what is going to happen is that if I'm to draw them properly with the typical X and Y in mind, where this is 0, maybe this is 200, this is 100, and this is 120 somewhere here, then it means that this diagram would go away. Let me take this one off a little bit so that there's going to be a drop to 100, and this will come to 120 somewhere here. So there'll be a drop like that, and then this becomes the new shape. Okay. So your actual M over EI diagram becomes this. Okay. So what it simply means that this 100 here is the one over here, the 120 is here, and this 100 again is down here. Okay, so this is a proper, so then this becomes your M over EI diagram. You don't need to go through all these steps. Once you draw your Benjamin diagram, this one, you can convert it straight to the last one. Okay. So this becomes the M over EI diagram, accounting for the different I values. Okay. So once we have that, then we can now load this on the conjugate beam. All right. So we are loading load load M over EI on the conjugate beam. Okay. So again, I'll draw this, but this time around to be a bit clean, to be a bit cleaner than before. Okay, so that okay, so I don't need to have all this plenty arrows and all this plenty stuff here. Okay. All right, so that's what we have. Okay, great. All right. So we know what the values are. So let me just write them down somewhere. Okay, let me just leave it so that I don't end up plastering the whole thing and making it look worse. All right. So this is the way to go. So I just load. So I have my support reactions will not really change. So I have something like this. Okay. So this is A prime, D prime, C prime, E prime, B prime. Okay. I hope things are looking nicer. Okay. All right. So all loads are moving away from the beam. So we have these different directions. Okay. All right. So let me draw an exaggerated version of what we are doing so that we appreciate a few things. Great. So this is what we have. Yeah, hey, this will do. Okay. So here's 200, different color. There's 200. This is 100, 120, 100, 200. Okay. All right. So once we have this, let me extend you a little bit. Okay, so that it looks somewhat symmetrical. All right. So now this is what we have. Now everything becomes geometry. All right, or math. All right. So we are looking for these support reactions. The goal is to find deflection at C. All right. But before then, we need to find VA prime and VB prime. Okay. So, I mean, these are, if you look at this carefully, we can divide it into a series of triangles and rectangles, right? Something like this, okay? I think this one will not be needed that much. So we can have about 1, 2, 3, and 4, okay? So with that in mind, things become a bit easy for us to work with. Okay. So we know that these are the various dimensions. 4 meters, 2 meters, 2, 2, and 4. All right. So let's go ahead. So summation of vertical forces equals 0. So V is downwards. So VA prime plus VB prime will be equal to. Now let's look at area 1. Area 1 is half base times height, right? Please, all of these are divided by EI. Okay, so I didn't bring my E over here, but I mean, they all have EI, okay. And because E is constant, we can ignore that for now, all right. So the first area is half base. My base is 4, and my height is 200, so 200 over EI plus second rectangle triangle. Again, half, the base is 4, the height is, so here the height should not be 120, okay. If you take rectangle triangle into consideration, the actual height of the triangle, this height over here is 20, right? It's 100 minus 120, becomes 20, all right. So I'll put that in here, 120 minus 100, so that at least we see what goes on, okay. Then rectangle 3, so this is 1, rectangle 3 will give us half base, sorry, to give us base times height. So with that one, our base is 4, our height is 100. So 4 times 100. Okay. So this is over EI. This also over EI. So this is the third one. Then the fourth one is pretty much the same as the first one. All right. So plus 1 over 2 times 4 times 200 over EI. Great, great. So from here, we can add everything up. So this becomes 400. 400 over EI. This will give us 40 over EI. This will give us 400 over EI and 400 over EI. All right. So and see 400 over EI plus 40 over EI plus 400 over EI plus 400 over EI. Okay. And this will give us 1,400, I think. Yeah. Over EI. Am I correct? Yes, I think I am, maybe. Okay. So we can do that. Then find VA. Okay. So if we want to find VA, we can take summation of moments at B to be equal to 0. Okay. We can do that one. Or due to symmetry. Okay. So due to symmetry of loading, and then let's say dimensions, it means that my VA prime is the same as my VB prime. Okay, so that's simply 1,400 divided by 2. Okay, so that'll give us 700 EI. Okay. I'm going to give you guys a little assignment. It's not really an assignment, all right? Okay, but try solving this particular problem on your own. And what I want you to do is, instead of using my symmetry approach, sum either moment about A prime or B prime. Am I correct with my... Let me make sure I'm correct before I end up with the wrong information. 400 plus 400 plus 400 plus 40. Oh, sorry. This is 240, not 1,400. Why? Okay. Right. So this should give me, divided by 2, I should I get 620. Okay. All right. So as I was saying, we should all try this with finding moment about either point A or point B. And then you can send just a screenshot of that to me on WhatsApp so I can see what you're up to. All right. This should be done, no, I'm sure by Monday should be fine. All right. So at least you can have more time to watch the Ghana game on Monday. Now, again, back to the problem. We want to find the deflection at C. So what do? We come to our conjugate beam, and then we cut a section through C. Okay. So we can use either the left-hand side or the right-hand side. Okay. Let's use the left-hand side. Okay. So I would end up with a beam like that. Let me exaggerate the size a little bit. So this is the bigger size. Then it comes down and it goes this way. All right, so it's half. All right, so this is how it will look like. Great. So here I have my VA prime, and I'll have my VC prime, and then I need to find this moment MC prime. Okay, so this is a cut section. Okay,
There'll
also be the horizontal section component of the reaction HC prime, but in this case is 0. So now we have all of these. Okay. So here, let's find moment about C. Okay. So it's easier to do summation of moment about C. Okay. Again, this is 200 over AI. This is 100 over EI, and this is 120 over EI. Okay, just so that we have those in mind. So, okay, this is fine. Summation of moment at C prime equals 0. So what do we do? All right, now we have all of these distances. Oops. So here's 4 meters. This is 2 meters. Okay. So let's start with the VA. So it becomes VA prime times 6 meters. And then that will cause a counterclockwise rotation about C. All right. Then plus the MC prime, because they are all going to be rotating the same direction. Then minus, so in this case, you can deal with the triangle separately. So you have this triangle here. So this is one triangle. Let me just shade it nicely. I become a painter all of a sudden. Okay. Then I can also have this rectangle here. Okay. Then another triangle in this small space. Okay. So you can look at it in this form, and I think it makes things easier when you do it that way. All right. So minus the big triangle on the left, it becomes half times a base of 4 times a height of 200 again over EI. At this point, you can what's the name? You can bring out the EI because you have been able to deal with the fact that you have taken care of all of that. Okay. Then times the moment arm, which would be 1/3 of 4 plus 2. Okay. So this is one set. Then let's deal with the smaller triangle at the top. Again, half times a base of 2, not 4, times a base of 2. And then the height will be 120 minus 100, so it becomes 20 over EI. Then times a distance of.
What be the registration?
We're not doing registration over here, please. Okay, all right. So then becomes the moment arm becomes 2/3 of 2 meters. So that is for the second one. And the third one, sorry, they're all minuses, will be for the just give me a second. Let me move this here. Okay, so the third one will be the triangle, sorry, the rectangle. So that will give us again minus the base. The base is what, 2, the height is 100 over EI. All right, then times half of 2. Okay. All of these should be equal to 0. It's a very long equation, but then the concepts are about the same. It's all about finding force times distance to get moment. And then if you go by that approach, it's easier. All right. So we know VA to be what? 620, right? So we can replace that by 620. We'll do all this math over here. Okay, let me just try doing that on my calculator. 4 divided by 3 plus 2 times 200 times 4 divided by 2. And I have what? So this minus 4,000. Take my answers with a pinch of salt, okay? So this is minus, sorry. Then I have 4 over 3 times 20. And this gives me 80 over 3. Then minus 200, I guess, over EI. So this is what? V, so 620, yeah, over 6, or times 6 divided by EI plus MC prime, and all of this equals 0. So you could see that we'll end up with one interesting value, all right? So in the end, MC prime and everything goes to the other side of the equal to sign. We'll end up with minus 2173. I think so, right? Yeah, over EI. Okay. So if we're given, so here our I would be ID, will be IAD or IEB, all right? So IAD or IEB is 270, and then our A is 200 GPA, okay? So this will give us minus 2173 divided by 200 times 10 exponent 6, then 270 times 10 exponent minus 6, and this should give us minus 0.0402 meters, which is the same as minus 40.2 millimeters. All right, so that's the way to solve these types of problems, right? It seems a lot because of the fact that we have different moments of inertia, all right? Otherwise, the idea is about the same, all right? If you're able to, because if you go by this approach, whereby you try to reduce everything to account for the different moments of inertia, it makes for an easier calculations. Over the years, I have come across students who maintain this shape. They maintain this shape right here, this particular shape. Okay. When you are relaxed, you can easily figure out by using the same shape for the conjugate beam calculations, but then under a bit of pressure and tension, you tend to forget that some of them are being divided through by 2. All right. So to avoid that potential mistake, the best approach is to go with the one on the side. So once this is fine, you just come and load your beam with the same shape, and then you can do your divisions and calculations, right? So here, pretty much the shapes that you might end up drawing would be rectangular, triangular, trapezoidal, and in some few instances, it might be, what's the name? Parabolic. All right, I think I have one example, or I should have posted an example like that on the V campus. All right. I think we spent a little over 1.5 hours or even more. We'll take about some 10 minutes break, and then we'll meet at what time? In the next 10 minutes. All right. If you have any questions, I'm around to answer those questions, but let's take about some 10 minutes break. All right.
Okay, thank you.
Recording. Great. So let's look at example 5, I think, yeah. Okay. So that one is a uniformly distribute. Sorry, it's a cantilever with a UDL halfway. All right. So these are the dimensions. This is 8 meters. This is 4 meters. It looks as though they are both the same size. A, B, and C. And I'm to find the slope at C and then the displacement at B. All right. So find theta C and then delta B. Okay. What's wrong with my fingers today? Okay. So here again, what do? We move things around and we draw a bending moment diagram. Okay. Bending moment diagram will take this shape. All right. So this is our bending moment diagram. Sorry, I didn't add the load. The load is, I think, 4 kilonewtons. 4 kilonewtons per meter. So the value here, EI is constant. So let me just put here that EI is constant. Okay, throughout. Constant. Okay. So this will be 22. Okay. 4, let me see. 4 times 4 times 2, 32, sorry. So yes, 32 over EI. And then this will give me 160 over EI, let's if I'm correct. Plus 8. Yeah, 160 over EI. Great. So we can see that so this has like kind of like it's a curve. And then here, let me just show the separation. Okay. So show the separation here. Okay. All right. So this should help us to easily draw it. Okay. So now I load this on the conjugate beam. Okay. So my conjugate beam would be like this. Then I copy, I'm just copy and paste. Hopefully I get it right. So, all right. So I load this on my bending moment diagram. Sorry, on my conjugate beam. All right. So now here I have A prime, B prime, C prime. Okay. So I need to find these reactions. If I can find, oops, shows me downwards. If I can find VC prime, then I can find my rotation. There's an MC prime. I don't need to find it because it's not part of the question I'm looking at, but again, I can still find it if I want to. All right. So let's look at VC prime. So here we have, okay. So summation of vertical forces equals 0. So again, please, the loads are moving away from the beam. That is the general idea or the general conventions used. Okay. So here, VC prime plus the area of the different loads. Okay, so let's start with the rectangular, which would be base times height. So the base is, so oops, what's wrong? So the base, let me just write this over here. This is 8 meters and this is 4 meters. Okay. So the base is 8 times a height of 160 over EI. Okay. Oh, sorry. What am I doing? Okay. Forgive me. So 8 times 32 over EI. Okay. Then the triangular load will be half times a base of 8 times the height difference of 160 minus 32 over EI. So that'll give me the other one. Then for the parabolic curve, it will be 1/3. So it will be 1/3. Okay, so this is the area of a parabola. 1/3 times 4 times a height of 32. Okay. So that should give us 0. Am I correct? Yep. All right. So our VC prime will then, let's see, plus 8 times 32 is 256 over EI plus everything in here will give me, I think 512 over EI plus this one also give me 128 over EI. So this should, yeah. So it means that our VC prime will be equal to, if you sum everything up, that will give us minus 810.67 over EI. So this is the same as theta C. Okay. Now we want to find so we want to find the moment at B, all right, which will give us the delta B. So again, we cut section at B. You can either use the right-hand side or the left-hand side. Okay, I think that in this case, the left-hand side is still easier. So I have a section like this. Okay. Then I have MB prime, MB, VB prime, and that's it. So these are what I have. And this end is 160 over EI, and this end is 32 over EI. So our so summation of moment at B prime equals 0. So it becomes MB prime plus the moment due to the various point loads. Okay. I mean the various the various triangular loads and then the rectangular load. Okay. So for the triangular, the rectangular load is the area is 8 times 32 over EI times a moment arm of half of 8. Okay. Then plus the triangular load, which is again the area is half of 8 times 160 minus 32 over EI times a moment arm of 2/3 of 8. Okay, so these two should give us 0. All right, so here from here, I hope I have my answers right. I doubt they might be right. Okay, so let me just do the math right now for us. Hopefully the math is right. If it's wrong, the information here is right. So If I get my math wrong, please forgive me. So 1024 over EI MB prime plus 160 minus 32 is 128 times 16 divided by 3 times 4. So this is 8192 over 3 EI. Okay. So this seems like a very huge value. So our MB prime will be equal to minus 3754.67 over EI. So once you have your EI in there, you can easily do it. Okay. So you guys should also try this. Maybe not now, later. Try finding or try delta C. Okay. So we should maybe after the class we try finding delta C. Okay. I think this should be okay. Are there any questions?
Sir, question.
Yeah, I'm listening. No question, no question.
Says a question.
Okay, sure. All right.
So why is that for the triangle? You have to subtract the 32 from the 160 instead of using the 160 directly.
Yeah, okay. That's a good question. So this is what I have. Okay. So this is there. So this entire height here is 160. This entire height is 32, right? But I'm breaking it into two. Okay, so it means that I'm dealing with this portion first. All right. So this portion is 32. So what should be this extra portion? Because height, let me say height 1 and height 2. So height 1 plus height 2 should give us 160. All right. So if the height of the rectangle is 32, then what would be the height of the triangle? This portion right here. Okay. All right. So that's how come I do the subtraction, because height 2 will be equal to 160 minus the 32. Is that clear enough?
Yes, very clear.
All right.
Thank you, sir.
You're welcome. All right. So it's a very good question. Please take note of it, because sometimes some students just mistakenly use the 160 for all. Okay. This is also easier. The area can still be, trapezium, right? Which is that what have A plus B times H, right? So your half A will be the 160, your B will be the 32, and then your H will be 8 meters. Okay. So this is the area. And I think a trapezium also has its moment of its moment arm, all right? So that if you are using a complete trapezium, it's one very funny equation. I don't even know what it is in my head. Right. It has to do, so if this is A, this is B, and this is H, there's a way to do it to get it. I think if you take the Hibla, I think the first page or so, or the first few pages also talks about finding how to get the moment arm for some of these things. Okay. There's a proof for it, but I don't think this class warrants us going through the proof. All right. So so in that case, I prefer to break it into easy to solve shapes, right? Triangles, rectangles, they are easy to solve shapes, right? Than these trapeziums and the rest. All right.